This is the CAT Vehicle, which stands for the Cognitive Autonomous Testing Vehicle. And it is not just named that because the school's mascot is a cat. This summer we've been working on creating a domain-specific modeling language for safe autonomous vehicle behaviors with dynamic constraint verification. Since I mostly worked on the modeling language, this video will focus on the language and deal very little with the verification. My partners in this research topic will be able to provide more information on the verification process in their videos. A modeling language, in the context of our project, is a graphical language that uses symbols and lines to build and represent vehicle behaviors. And now for the weather. Welcome to sunny Tucson, where there isn't a cloud in the sky. Uh-oh. Now back to your regularly scheduled programming. Would you like to be able to program an automated vehicle? Would you, say, like to be able to write a little program on your computer to tell your car to drive forward for 60 seconds at 4 meters per second? Well, let's see how it can be done. You could use C++, however this would require a good understanding of both the language of C++ and the in and outs of the networking behind the scenes done by the Robot Operating System, or ROS, that drives the car. With a lot of training and practice, it still takes over 5 minutes of real time just to tell the car to drive forward for 60 seconds. There has to be a better way. Introducing WebGME and the CAT Vehicle modeling language. With a basic understanding of any programming language and a bit of instruction, anyone can create even complex behaviors for the CAT Vehicle in no time at all. Watch as the behavior goes from 0 to done in an instant. Just over 2 minutes. That's an increase of efficiency of over 200%. But wait, that isn't all the CAT Vehicle modeling language is good for. The model interpreter that runs the commands in the car checks the safety of the commands at runtime and will actively modify them to ensure the safety of the car and the testing environment. Here's the simulated CAT Vehicle. Since there's only one real-life CAT Vehicle, we have to test all of our unsafe behaviors on this one. Sorry, simulated CAT Vehicle. Let's see what happens with the behavior written in the previous demonstration when it confronts an unexpected object in its environment. It plows right through it. But what if the car were going even faster? Uh-oh, that's not good. Let's see how the interpreter does. It approaches the object nice and slowly and stops before anything can go wrong. If the object is a potential danger, the car approaches with caution and then resumes normal behavior once the object is not in range to be hit. Another concern is turning and rolling over. Watch as this native code drives at full speed in full turn. The car doesn't stand a chance. The interpreter, on the other hand, forces the car to drive at a slower speed depending on the wheel angle. Look at that beautiful circle. This is the follower behavior. It checks if an object is within a certain range, then if the object is in front of it, it drives forward, else it steers and drives in the direction of the object, and thus achieves the behavior of following. And it is this behavior that we use to test on the car in real life. That's enough simulation. Let's see the code run in real life. Here at the testing parking lot, the car takes full control, and the object being followed is one of us. This might seem dangerous, but it really isn't. The software isn't the only thing keeping us safe. There's a big red button in the car that when pressed stops the vehicle in an instant. On top of that, the car is never instructed to go over 2 meters per second, roughly 5 miles per hour. Any able-bodied research assistant should be able to easily outrun it. With this in mind, let's start the test. is terminated and the test ends a success. And that's been my project. With the CAT Vehicle modeling language, anyone can create safe behaviors for the CAT vehicle.